This video tutorial is focused on harvesting the energy from the sun, harvesting the energy from the wind, and harvesting rainwater. The architect and owner, when planning to construct a building or designing it, have to think about the energy efficiency of this specific house. Now we have the Armadillo and Onion inspired sleep out. You can get the information on the other video tutorials on this channel, but I'm going to continue now. The energy efficiency which we will look at will be the photovoltaic panels, those black panels right there. Photovoltaic meaning photo light, voltaic meaning the sunlight is converted to electricity and stored into batteries, and that power is supplied to the house for electricity in general. We have wind turbines, smaller wind turbines installed on the roof here, and we have one larger wind turbine. There could be more, but this is just to illustrate. So we are expecting the wind to blow in this direction. If you look at the curves in this direction, the large wind turbines, the head would rotate and face the wind. Now we also have an underground, this is an underground rainwater storage tank, but we also have a storage tank right there. It's translucent, you can see the water. So the water, the rainwater, or the rain which fell on the roof would be channeled into these long water tanks. So we have two types of water tanks. The large underground one for maybe the veggie gardens when large amounts of water is required. We have these smaller tanks. Now these tanks, we could have them in different compartments. At the top here, this water, grey water, not filtered, could be channeled to the cisterns in the toilets, for instance. Now gravity plays a role here because that water will automatically just run down the pipe because it's higher than the cisterns of the toilets, which is probably around about here. The other area which I would like to look at is the solar thermal panel. Now this panel here, or this arc here, is covered with pipes. It's like black tubes, plastic PVC pipe filled with water, and the sun would heat it up, and there's a thermostat, and the thermostat with electronics will communicate with a pump, and that pump would take this water to the hot water cylinder somewhere inside the building. Now all it does is it preheats the water, and that water gets sent to the hot water cylinder, making it more energy efficient because the hot water cylinder don't have to work that hard because it receives hot water on a warm or a hot day. We have the energy, fuel and end use in New Zealand homes diagram in front of us, being prepared by the physics department of the Otago University in New Zealand. This is a summary of power or energy use in New Zealand, and it is very useful when making decisions about passive solar design, sustainable architecture, design of buildings, and so on. Let's have a quick look at it. Right at the top we can see we have a 20% on solid fuel, that's wood, coal, fuels. We have LPG and gas being used around the house, which is about 11%, and then electricity, which most homes use. That's the local electricity company which provides power through cables, electrical cables. We usually say it's from the grid. And if we move down, we can see that the heating of a building is about 34%, which is the highest or the biggest component of power or energy being used. So It's electrical heaters, heat pumps, wood burners, multi-fuel burners, gas heaters, etc. Now, the second area or percentage is 29%, and that's for water heating. That's just having hot water available 24 hours a day, every day of the year. So it's hot water cylinder, wetback, and so on. On 19% sits the appliances, where we have dishwashers, washing machines, dryers, televisions, computers, and so on. On the far right, we have an 8% on lights, which is pretty low, just lighting during the day and which we use more during night, obviously. And then we have a 10%, which is just like a general for other, which just fits into the other category. In the next part of this tutorial, we are going to explore some data which are weather and climate related for the Hamilton area in New Zealand. We are going to look at rainfall, sunny days, etc. But let's start from the weatherandclimate.com website, and we are going to look at the average minimum and maximum temperatures over the year. So summer is in January and winter is June, July in New Zealand. The red is the top temperature in Celsius and the blue line is the minimum temperature. So we can see that the temperature ranges from about 22 degrees right there down to about 14 degrees in winter, and the minimum temperature is about 14 degrees Celsius, and it goes down from summer to winter to probably about 5, 6, 7 degrees. Now it's important to make a note of that when you do your research, because as the architect or designer you need this information. But let's continue, because we need more information and more data to make informed decisions about energy efficiency in sustainable architectural design. The next chart shows us the average monthly hours of sunshine over the year. Now that's important, because if we're going to install some photovoltaic panels, we need to make a decision. Is it worth installing it? Should we install many? And of course we will also use an online calculator later in this tutorial. Quickly, we got the hours on the left and the months at the bottom, summer and winter right there. So we can see in summer we have about 220 hours, that's monthly hours in summer, and then it goes down to about 140 hours per month. Now we need to make some notes on our pad just on this information, because it's all about Hamilton. That's the location in the North Island of New Zealand. Our next chart is the average percent of sunshine over the year. This is the mean percent of sunshine hours during the day. This is per day. So we got summer in January and winter, June, July, and December over there. We have the sunshine percentage right there. Now remember, this is sunshine hours per day or during the day. So we can see there's not a big fluctuation here, from about 58% to about 46, 47%. There you can see it. So New Zealand is also known as the land of the long white cloud, which means there's a lot of clouds here. So about 40%, if we deduct that 40 from that 60, that's that part over there and up, we will have clouds. So we know now that about 58 to 47, 48% we will have sunshine hours during the day. The rest would be cloudy. The water temperature over the year, that would influence like the water in our water tanks, the water being sent to the hot water cylinder. That's important information, and we can get that information from this chart right here. Again, the months at the bottom, the temperature on the left hand side here, and this is the monthly mean water temperature. You can convert it to Fahrenheit by just clicking there, just like to show you, but this is in Celsius right here. So we can see over the year, in summer it starts here at about 18 degrees, 17, 18 degrees, and that's during summer. It goes up during March. March is a very hot month in New Zealand, a warm month, and then it drops down to July, June, July, August, the colder months, or winter, to probably about 15, 14 degrees. And that's important information. Again, just jot that down, just make that note on your notepad. Our next chart shows the average monthly precipitation, precipitation meaning rainfall over the year. That includes snow, etc. Now this is the mean monthly precipitation, including rain, snow, hail, etc. Now it's in millimeters right here on the left, and on the horizontal bar we have January, February, the months again, summer over here, and winter right there. Now we can see that the most rain in New Zealand is received during the winter time right there. That's where we get the most rain. And then again, that's that interesting month, March right there, where New Zealand would, or Hamilton rather, would receive lots of rain. Make a note of that. You can even jot down just small notes, maybe summer, winter, and so on. Our next chart is the average monthly rainy days over the year. So this is the number of days each month with rain, snow, hail, etc. It is the number of days each month. So let's have a look in January. We have about 10 rainy days out of the 30. There are 30 days in a month, so a third of the days will have rain, snow, hail, etc. Now it increases from summer, as expected, to around about 15, half the month, we will have lots of rain. Now New Zealand is famous for its rain during winter, so, and you have like 4 seasons in one day, a lot of rain and sun at different intervals, 1 hour intervals. Very interesting. But from this information and from this chart, we can make a very important decision about the size of the water tanks, and is it worth investing it, and where should we put it. There's a lot of things which we need to consider. The average wind speed over the year is important when considering wind turbines, smaller and larger wind turbines. There's a lot of things we need to think about, but let's just have a look at this chart. Pretty stable chart. The wind speed here is in meters per second. Now in summer here we have about 4 meters per second in January. Now 1 second is if you count 1,000, that's a second. If you count 1,000, 2,000, those are 2 seconds. So if you take 4 quick paces, walk 4 paces within a second, you have to be very fast, almost running. That will give you an indication of the wind speed. It's slightly faster during the September, October, November, December months, and of course the month with the lowest wind speed is June. In the next part of this tutorial, we are going to look at the electricity bill of a typical 3-bedroom home with 2 occupants in the Hamilton area. Now we're not going to look at all this information in detail. All we're really going to focus on is the kilowatt hours. We got 233 kilowatt hours, we got 154 kilowatt hours, and we got 387 kilowatt hours. If we add them all up, we get to 574 kilowatt hours for the month in March. We can also see the unit prices here, which is interesting. $29.91, $21.96, and 30 cents. So if we multiply the kilowatt hours with that unit, that's the amount which we get. So if we add it all up, including GST, we get to an amount of $111.63, and that's the bill for this household for this specific month. This is important information when installing photovoltaic panels, because once you know what the output of the photovoltaic panels per year would be, or per month, we can determine if this house could run off the grid. In other words, would the sun be able to run the house and we don't have to pay any more electricity bills? And that's typically when we refer to a building as off the grid. Just make a quick comment about this part of the bill right here. I'm just going to scroll down quickly and let's have a look at that. So this histogram, you can ignore this left side. Yeah, it's just the units. That's dollars over there. But the point I want to make is we're looking at the different seasons starting in May 2015 to May 2016. We have winter here. We can see how the histogram spikes. In other words, more energy being used specifically to heat the building. And then it drops over the warmer months during summer. And then it spikes again in January. What we know from the owners or the occupants of this house, that a spa pool was running during January, and that's the reason why it spiked. Now we could make a decision here, because the people use a spa pool, we could use a solar thermal panel. That's the system where the pipes are filled with water, the sun heats it up, and that water gets sent to the hot water cylinder, but it could also be sent to the spa pool. So a saving is possible by just planning and installing different systems. In conclusion then, the Armadillo and Onion inspired sleep out could be powered by sustainable features like the photovoltaic panel, which we've discussed. So if we have about 5, 6, 7,000 kilowatt hours per year, that would be enough to power this house. Additionally, we could use the wind turbines and the smaller wind turbines to provide additional power to charge those batteries and have a bit of a surplus for power use in this building. The rainwater system, the underground water tank, as well as the smaller tanks installed in the cavities or these compartments of the roof, could provide water either to the veggie gardens or to the cisterns of the toilets in the building and general use. A final comment then is on the choice of building materials for the sleep out. Passive solar design requires building materials that are a good heat sink. A good heat sink meaning that the sun would be absorbed by the different building materials, in this instance concrete and steel, absorb that heat and releases it slowly during the day, heating up the building in winter, for instance. During summer, of course, we'll have the deciduous trees and these panels or screens which would screen the sun out. But let's continue with the winter scenario where we want to heat this building, where most energy is required. So the walls of this building is made of concrete and steel reinforcing. The roof panels also made of concrete and steel reinforcing. These layered panels like a typical onion. And the floor is also made out of concrete with steel reinforcing. Just something interesting I'd like to mention. If we add a geofoam, it's just like a white polystyrene or white foam, looks like typical packaging material when you buy an appliance or something. It's normally packaged in it, but this is a high density and is extremely strong. So if we install this under the floor, before we cast the concrete right there, before we cast that concrete, this is the geofoam layer. It means that the building will literally float on the polystyrene or the geofoam. That's just an additional insulator for this building. But let's continue. So we have seen that the solar thermal panels or photovoltaic panels could provide about 4, 5, 6,000 kilowatt hours per year, which could power this house. Additionally, we could get additional power from the wind turbines, the large ones, and the smaller ones on the roof, maybe another 2,000-3,000 kilowatt hours per year, depending on the wind conditions and so on. The third component is the harvesting of rainwater. So we have this tank, the underground tank, which could provide water to the veggie gardens and for general use in the building. The water tanks in the roof here could provide grey water, unfiltered water, to the cisterns of the toilets. So in short, we can see that the building could be powered by the sun, and we could be off the grid and not receive any electricity bills. Something else I'd like to throw in, just consider you have an electric car or a hybrid car, meaning it runs on fuel and electricity, either or. You could power this house with your electric car in an emergency, but you can also charge and power your car from the sustainable systems installed in this building. Now that's a wonderful scenario to think about, not receiving any power bills, but to be fully self-sufficient and independent, saving the resources of our precious planet.